Hello and welcome to today's IWCS webinar. My name is Connie, and I'll be your WebEx Cisco program producer for this event. Now, I'm pleased to turn the webinar over to Ed Vinton, your IWCS moderator. Ed, please go ahead.
Thank you, Connie. Our IWCS webinar series event is hosted by the International Cable and Connectivity Symposium. I am Ed Fenton, a cable industry advisor working with the IWCS team. As Connie said, if you have questions, please use the Q&A box on the bottom right of your screen to post a question anonymously. If you wish to contact the presenter or IWCS after the presentation, you will be given the contact points at the end of the webinar. Please note that IWCS does not distribute the presentation slides from either our conference sessions or these webinars. However, please feel free to contact the presenter directly, and they will respond individually to you. Today, we welcome Florence Akinoyen, PhD student, de Montfort University School of Engineering and Sustainable Development in Leicester, United Kingdom, who will be presenting her paper on long-term effect of thermal variation on the performance of Ethernet cabling. Florence Akinoyen graduated with a Bachelor of Technology in Computer Science from the Federal University of Technology, Akure, FUTA, Ondo State in Nigeria. She received her Master of Science degree in Communications Engineering from De Montfort University in Leicester in 2011. She is now a PhD student studying the impact of temperature on data cable performance. Florence, we welcome you today to present at today's IWCS webinar series event.
Thank you very much, Ed, for the nice introduction. Hello, everyone. Thanks for joining us for today's webinar. The main thrust of today's presentation is to look at the immediate effect of temperature and the long-term effect of thermal variation on the performance of balanced UTP cables that are currently used for power over Ethernet applications. We will also be looking at the effect of temperature and the effect of thermal variation on the performance of different dielectrics that are used for conductor insulation in data-grade cabling. So today, we're going to start by looking at the motivations for these studies. We know that the information technology sector has undergone some significant revolutionary periods in the past decades. As a result, there are now increasing interest in high-frequency applications. The drivers of these high-frequency applications are mobile networking technology, cloud computing, Internet of Things, and so on. As the information technology advances, Ethernet, as a foundational technology for the whole connected world, has also continued to evolve. Similarly, the existing wireless technologies are also evolving. The speed of Wi-Fi is now growing beyond the speed of the existing 802.11ac Wave 1. Through the convergence between the wired network and wireless network, power over Ethernet technology is also playing pivotal roles in supporting in-building mobility. We know that power over Ethernet technologies allow electrical power and data signal to be transmitted on the same Ethernet cable without the need for a separate electrical outlet. So, the adoption of PoE technology is a cost-effective solution of providing electrical power to the network devices, such as wireless access points. Although, due to the benefits of power over Ethernet technologies, there are not power-hungry devices in the market that want to take advantage of benefits that PoE offers. Example of power-hungry devices that we have in the market now are the dual-band wireless access points, high-definition TVs, outdoor cameras with heaters and blowers, point of sale, and so on. As a result of this, there are now increasing demand of high-power standardization from the PoE standard borders. Also, With the upcoming speed of the 802.11 AC Wave 2 and 802.11 AS, one may expect throughput from the smart users and smart devices on the network to be high. In this regard, we expect loads of data to be transmitted through the Ethernet cables that are connected to the wireless access point. The challenge is that most of the install base of PoE are predominantly with Category 5E and Category 6 unshielded twisted pair cables due to cost. Also, these lower categories of cables are specified for a maximum throughput of 1 gigabit per second, but the speed of Wi-Fi technology continues to grow beyond 1.3 gigabits per second, even growing beyond the speed of the NBC technologies. With many businesses now going online, cabling with high bandwidth will be required to move data across the network. So, to transmit high electrical power and high-frequency data concurrently, a high-performance cable, such as Category 6A, is recommended. Category 6A cabling can provide high bandwidth required and remote powering capabilities that the emerging applications require. However, it is important to understand the thermal performance of the cabling over a long period of usage. With the standardization of the electric power now heading towards 100 watts, the effect of temperature arising from 100 watts can affect the quality of the data signal passing through the bonded Ethernet cables. At high frequencies, the effect can be significant. This is because at high frequencies, the frequency-dependent effects such as ringing, crosstalk, skin effect, and dielectric loss become prevalent. For example, insertion loss due to dielectric loss is proportional to frequency. Since it is necessary for copper cabling to provide high-speed, low-latency access to the Internet while delivering high electrical power to the network devices, it is also paramount to deploy good quality cables that can serve these purposes. For the past few years of our extensive study on the heating effect due to power transmission over balanced twisted pair cabling, we have observed that temperature rise due to the passage of high current in the cable affect the performance of the cable, as we will see in the subsequent slides. This effect depends on the conductor sizes, the installation practices, cable design variations, and material composition. If these factors can be controlled, however, the optimum performance of PoE channel can be achieved. Now, let's look at the studies that we've conducted in the past. We will first of all look at the immediate effect of temperature on bonded Ethernet cables. In our research work published at the IWCS conference in 2014, cable bonded heating was assessed at different power levels. That is at 34 watts, 60 watts, and 100 watts. The objective of the study was to assess the thermal limits of different categories of Ethernet cables in terms of material types, cable construction, and installation environments at different power levels. As shown on this slide, we tested both shielded and unshielded twisted pair cabling under two installation environments. We considered bonded cables installed in ventilated spaces, which we called free air heating here. We also tested cable bundles installed in unventilated spaces, such as cable bundles installed in some pathway systems, such as conduits, and at the same time kept behind wall, ceiling spaces, or thermally insulated environments in general. The amount of temperature measured during this test are plotted in the two figures shown on this slide. As we can see on the left figure, it was found that cable bundles tested in the ventilated spaces produced less temperature rise when compared with the temperature rise on the insulated cable bundles. Thermal impact of high power such as 100 watts was found to be more pronounced with the insulated unshielded twisted pair cabling than the shielded twisted pair cabling. As can be seen, temperature rise on the insulated cable bundles exceeded the defined operating temperature of 60 degrees C for all cable constructions at 60 watts and at 100 watts. It was also found that high power transmission over thermally insulated 37 cable bundles played a significant role in the immediate physical failure of the cable. In fact, when the temperature rise on the insulated unshielded twisted pair cable reached a temperature at which the dielectrics were extruded on their copper conductors, that is 135 degrees C rise above ambient, the deformation of the dielectric was observed. The dielectrics melted and a short circuit occurred. Having seen this effect, the important question now is whether the existing dielectric can support the next generation of PoE at 100 watts. This slide also shows the effects that we want to look at. In this current test I've shown on this slide, the effect that we want to look at is the effect of thermal variation and insulation condition on the transmission parameters of the cable. This work was presented at the IWCS conference in 2015. The effect of changes in the environmental temperature and the performance of Category 6 UTP permanent link was studied. And the reason why we have conducted this study was because in some installation environments such as stadium, airports, shopping malls, the local ambient temperature on the cable is not always constant. The occasional increase in user density on the network can trigger a rise in temperature on the cable. Additionally, wireless access points will be required to function in increasingly remote locations and harsh environments. So, the variation in the ambient temperature can influence the mechanical behavior of the cable. So, to study this scenario, as can be seen in the setup picture shown on this slide, Category 6 unshielded twisted pair cable was kept loosely inside a constructed heat chamber, and the cable link was heated externally. That is, the cable was not energized, but was heated externally with some heating elements placed inside the heat chamber. The cable was repeatedly heated with a temperature range of 20 to 70 degrees C, and temperature was allowed to cool naturally. The cable transmission parameters were measured with a DX 5000 cable analyzer from Futp Networks. As shown in the return loss plots displayed on the right, a noticeable permanent reduction in the return loss margin of the Cat6 UTP permanent link was observed after the first heating of the cable. The permanent reduction is also apparent in the return loss margin obtained for the orange and the brown pair in the cable. We've seen the effects of thermal variation on a cable bundle that was insulated and kept in a thermally insulated environment. Now, we want to look at another insulation environment where only a portion of the cable was thermally insulated. We have simulated this type of installation environment because cables are sometimes bundled from the telecommunication room before branching off to feed different network devices. In some installation environments, a portion of the cable can pass through thermally insulated environments or perhaps a fire barrier or many more. This causes localized heating of the cable bundle. We wanted to find out how the thermal variation on the cable will impact the performance of the link over a long period of time. For instance, if Category 6A cable are to be deployed in this type of installation environment, can the specified temperature limit of 60 degrees C have a long-term effect on the cable performance? Over a long time, can the thermal variation on the cable affect the dielectrics of the cable, causing the performance of the cable to drift? So in providing answers to these questions, Category 6A Futp permanent link was tested to study the long-term effect of thermal variation on the performance of the cable link. As can be seen in the setup picture, a portion of the cable was heated externally inside a constructed heat chamber. The maximum cable heating temperature was just 60 degrees C, which is the maximum temperature limit specified by the POE standard. 40 heating and cooling cycles were performed on the cable, as reported in the study, although the measurement is still ongoing. In the first 20 thermocycling, the cable was heated for 24 hours and cooled naturally for 24 hours. However, after the first 20 cycles, the heating period was changed to 1 week heating period to observe the effect of prolonged heating rather than the intermittent heating that was performed for the first 20 cycles. The drift in the transmission parameters of the cable link was measured with a DX 5000 cable analyzer using both Class EA ISO test limits and the TIA Cat 6A test limits. The return loss margin and the insertion loss margin for the 40 heating and cooling cycles are presented on this slide. As can be seen on the two plots, the green dots represent the baseline margin measured when the cable had not been heated at all. The red traces represent the measurement made during the heating cycles, while the blue traces were the measurements obtained after the temperature on the cable had reached near the room temperature. It is apparent that return loss margin increased initially, remained constant for some cycles, and later reduced progressively. The distinct protruding red dots shown in the left figure could be due to the change in the heating period of the cable. At this point, the electrical lines of the cable and the impedance also change, as we will see shortly in this presentation. Insertion loss margin, however, reduced progressively from the first heating cycle. But generally, the worst-case return loss performance of the permanent link was measured when the cable had cooled down naturally. However, the insertion loss performance is opposite to the return loss performance. The worst insertion loss performance of the permanent link was obtained with temperature of 60 degrees C. In the previous slide, the return loss margin was shown, but in this current slide, the actual return loss traces for the heating and the cooling cycles are presented. By following the red arrows, we can observe a distinct resonance that was measured after the first heating of the cable, that is at heating cycle 2. The distinct resonance that was measured during the second heating of the cable can also be observed in the equal level transverse conversion transverse loss plots shown on this slide. I'm referring to the red protruding trace in the figure. The ELTCTL is one of the parameters used for testing the balance of the cable link. It measures the amount of mode conversion at the far end within a pair of the cable link. The green trace was the baseline measurement. The red traces were the measurement made during the heating cycles, while the blue traces were the results obtained after the cooling of the cable. The other two interesting resonances occurred at heating and cooling cycle 39, where the electrical lines and the impedance of pair 1, 2, which is the orange pair, have also changed, as we'll see also shortly. We've seen the return loss margin results. We've also seen the return loss traces. The actual values of return loss measured at 136 megahertz using the Class EA ISO limits as shown on this slide. These results were obtained from the main and the remote side of the link using the cable analyzer, as can be seen from the baseline values on the left up to the values obtained at the cycle 40. The result shows the reduction and the drift in the return loss performance of the permanent link as the portion of the cable was heated and cooled repeatedly. The amount of return loss degradation obtained with both TIA and ISO test limits are compared on this slide. An agreement between the degradation obtained using the two standard limits can be seen. To clearly observe the drift in the return loss performance of the permanent link, we have plotted just a few of the traces as shown on this slide. The baseline measurement results are plotted as blue traces, while the last measurements obtained are the red are in red color. A shift in the signal trace to the high frequency can be observed from the baseline measurement up to the last heating and the cooling cycle. A reduction in the signal amplitude is also apparent. The shift in the signal trace could be as a result of the change in the dielectric constant of the conductor insulation. This is because the speed at which a signal propagates depends on the properties of the conductor insulation, such as dielectric constant. For instance, if the dielectric constant increases, the velocity of propagation of the signal will reduce. Also, if the medium of the propagation of the signal changes, the wavelength will change. If the wavelength reduces, for instance, the frequency of the signal will also change. Now let's look at the observed changes in the electrical properties of the cable link. As I've explained earlier on in the test setup, a reduction in the electrical length of the orange pair, which is the pair 1-2, was observed at the transition between the heating periods. Evidently, in the bottom left figure, the resulting impact of the decrease in the electrical length of pair 1-2 was a decrease in the propagation delay. The propagation delay on the orange pair reduced by 1 nanosecond. The figure on the bottom right also shows that delay skew on the longest pair, which is pair 3-6, increased as a result of the change in the propagation delay on the orange pair. It is obvious here that the dielectric constant if the dielectric constant increases, the velocity of propagation of the signal will reduce. A lower velocity of propagation is likely to contribute to a delay for a given length of pair. The major concern here is that this type of performance has been observed on the category 6 UTP link also. The implication of this is that if all the pairs are affected differently in the cable, delay skew could increase more than this. And when data is transferred along 4 pairs simultaneously, this might have effect on the maximum achievable data rate. Now that we have seen the significance of dielectric constant on the electrical properties of the cable, any changes in the dielectric constant means that the capacitance will change. When the capacitance changes, well, the impedance is going to change. Changes in impedance will affect the return loss performance. As we have seen, the return loss performance of the cable link drifted with thermocycling within 60 degrees C. If the dielectric constant increases, the capacitance will increase, the impedance will reduce. Impedance mismatches will cause reflection of the signal on the channel, and the amount of reflection on the channel is measured as return loss. As can be seen on the bottom right, the impedance varied from one heating cycle to the other. The impedance on the link reduced after the first heating of the cable. The impedance also increased at the transition point where the electrical lines change, as we have observed in the distinct resonance measured showed earlier on. The next slide shows the insertion loss performance of the Category 6A Futp permanent link. The green pair 36, is the longest pair in the cable, so its insertion loss obtained during the heating and the cooling cycles are plotted in the two figures on this slide. The deep blue traces in the two figures were the baseline insertion loss measured before the heating of the cable began. As can be seen on the left figure, the insertion loss of the permanent link increased with temperature of 60 degrees C and continued to increase from one cycle to the other. The insertion loss obtained when the temperature on the cable had returned to near the room temperature is also shown in the right-hand figure. As can be seen, insertion loss continued to increase from one cycle to the other, even at room temperature. The value of the insertion loss at 500 megahertz are shown below the two figures. The third column shows that insertion loss increased more during the heating cycles than due to the cooling of the cable, as shown in the last column. The significance of dielectric constant and dielectric loss in the calculation of the attenuation constant is illustrated on this slide. Any changes in the imaginary part of the dielectric permittivity will impact the whole channel performance. This next slide shows the percentage of the signal power loss measured during the thermocycling. As shown in the results, the percentage of the signal power loss increased as the cable was repeatedly cycled. The power loss increased from 0.4% that was measured during the first heating of the cable, increased to about 3% as seen for the 20X heating cycles, and up to about 5.5% for the last heating cycle. Although smaller, similar trends in the power loss for the cooling cycles can also be seen in the three figures to the right. This shows that Ethernet cables must be designed to minimize power loss in order to achieve high data rates on the cables throughout the design useful life of the cable. Having seen the changes in the Category 6 UTP permanent link and Category 6A Futp permanent link, the relevant questions to the industry are as follows. Considering the effect of bonding and installation conditions, can the specified temperature limit of 60 degrees C have a long-term effect on cable performance? Can the temperature rising from 100 watts induce accelerated aging in the compounds used for cable dielectrics, for example, causing migration of the plasticizers? Or will the flammability factor be affected over a long-term heating, posing a risk of fire accidents? Can the existing cable infrastructure support the paradigm shift in the global mobile networking technology? Hence, the focus of this research is to examine the dielectric properties of different insulation types used in Ethernet cabling to understand what the causes of the observed issues are. The reason for this is because most cables' transmission parameters are determined from the dielectric permittivity. As a result, there is a need to understand the electromagnetic behavior of the cabling. However, we want to study the dielectric permittivity first. Since dielectric permittivity is both frequency and temperature dependent, how can the properties of this dielectric be reliably measured? In the work presented at the IWCS conference in 2016, we established cavity perturbation method based on the ASTM standard as the most accurate test methodology for testing of the material properties. We designed 1 GHz, 2.4 GHz, and 5 GHz rectangular resonant cavity using analytical approach for the material testing. The simulated and the fabricated rectangular resonant cavities are shown on this slide. One of the primary requirements for accurate dielectric property measurement using cavity perturbation method is to place the sample in a region of a uniform and maximum electric field inside the cavity. This position was verified by using a single PTFE rod sample to obtain the field distribution inside the cavity by measurement. The most accurate dielectric constant for this single generic PTFE rod sample was obtained when the sample was placed at the center of the cavity. This accurate position for the dielectric placement was also validated by simulation using CST Microwave Studio. The field distribution inside the simulated and the fabricated rectangular resonant cavity are shown on this slide. An agreement between the field distribution was established, so all the samples measured were placed in the position of the maximum electric field. As shown in the picture below the cavity, the dielectric tested were the samples of materials extracted from the data grade cables. The dielectric samples were obtained from the lower categories of cables such as Category 5 UTP, Category 6 UTP, Category 6 FUTP, and they were also obtained from higher categories of cables such as Category 6A FUTP, Category 6A FFTP, and Category 7 SFTP cables respectively. We tested all the dielectric samples at room temperature first to obtain the baseline dielectric constants across the 3 frequencies. We then tested the samples with temperature up to 60 degrees C, but only the Foamed-Skin high-density polyethylene was tested up to 90 degrees C. To obtain the temperature of the dielectric for the calculation of the dielectric constant due to heating, a wireless temperature sensor was placed inside the cavity to obtain the temperature distribution inside the cavity. We also placed thermocouple sensor outside the cavity to obtain the temperature distribution outside the cavity. We compared the 2 temperature distribution and we found agreement between the 2 outputs. So we used the temperature obtained outside the cavity for the calculation of the dielectric constants. No thermocouple sensor was placed inside the cavity when the samples were tested in the oven. We calculated the values of the dielectric constant using the standard ASTM equation. Now let's look at the results of the dielectric constant obtained at room temperature and across the 3 frequencies. As shown in the left figure, at 1 GHz, the dielectric constant of the samples obtained from the higher categories of cable was lower when compared to the dielectric constant obtained from the samples obtained from the lower categories of cable. It is also apparent that the dielectric constant for the foamed dielectric samples is lower when compared to the dielectric constant of the solid materials. The lower dielectric constant of the foamed material indicates the reason for the foaming of the dielectrics. This trend was consistent for the 2.4 GHz case and the 5 GHz case. The lower dielectric constant at room temperature, it can be seen on this slide. I've shown the assessment of dielectric constant at 60 degrees C. results of the assessment of the dielectric constant at 60 degrees C are shown on this slide. At 1 gigahertz, the dielectric constant of the solid materials obtained from Category 5E and Category 6 cables reduced with the effect of temperature at 60 degrees C, whereas the dielectric constant of the materials obtained from Category 6A and Category 7 cables increased with the effect of temperature at 60 degrees C. At 5 gigahertz, however, when the frequency of the field was sufficiently large, the dielectric constant obtained for all the dielectric reduced at 60 degrees C. The dielectric constant of the foam dielectric was found to be more stable when compared with the dielectric constant of the solid materials. We also observed correlation between the trend in the return loss margin of Category 6 UUTP and its dielectric behavior. This is also shown in the return loss margin obtained from the orange pair and the brown pair in the Category 6 cable. The dielectric constant of the Foamed-Skin high-density polyethylene was assessed at 60 degrees C with thermocycling across the three frequencies. As can be seen in these three figures, the dielectric constant of the Foamed-Skin high-density polyethylene changed within the first heating of the material across the three frequencies. Additionally, the dielectric constant of the Foamed-Skin high-density polyethylene changed within the first heating of the material, and at 5 gigahertz, a non-reversible modification in the dielectric constant of the sample can be seen with the effect of temperature at 60 degrees C. We also studied the dielectric constant of the Foamed-Skin high-density polyethylene at room temperature up to 90 degrees C, and from 90 degrees C back to the room temperature with a step of 10 degrees C. The transient analysis of the dielectric constant across the temperature range and at 5 gigahertz is shown on this slide. As can be seen on the bottom right of the figure, the 1.74 in green color was the dielectric constant obtained before the heating of the sample began. As the material was heated in the oven, the heating of the dielectric at 30 degrees C caused the dielectric constant of the material to increase from its baseline value of 1.74 to 1.76. The dielectric constant initially increased, decreased at about 85 degrees C. Moreover, when the temperature of the oven was turned off, the dielectric constant began to increase again. It can be seen clearly in this result that the dielectric constant of the Foamed-Skin high-density polyethylene varied with temperature at 5 gigahertz. However, the dielectric constant increased permanently with thermocycling. In summary and in conclusion, some immediate and long-term heating effects on cables' transmission parameters have been observed. The immediate changes in the cable performance raise a question of whether the cables need to be pre-aged before conducting link or channel certification tests for the new installations. Permanent changes to the value of dielectric constant was also observed. If these cables are to carry power and therefore be subject to multiple self-heating cycles, are today's compound the right ones for tomorrow's network speed? Since the changes in the cable transmission parameters could be due to changes in the material properties or changes in the cable geometry or both, characterizing the root causes of signal degradation is paramount. So our future work will examine and relate the contribution of dielectric degradation to the observed changes in the cable performance. We would like to thank the Excel Networking, Fluke Networks, KIMOS, IWS, and IWMA for supporting this research. And I thank you all for your attention.
Florence, thank you very much. At this time, we will ask as many questions from the attendees as time permits. I'd like to start with this first question, which asks if you can go back to slide 8. The question refers to slide 8, and it said, what are the current levels of the slide 8 data?
I'm just going to scroll down to slide 8.
Yep, thank you. There you go. Okay.
Yes.
So the question reads, what are the current levels of the slide 8 data?
The current level of what?
What are the current levels? That's the incoming.
The energized current level for this measurement, is that what?
It sounds like it, yes.
Well, the current level for IEEE, the standardized current level for IEEE 802.380 is 600 milliamp per pair. But to energize the cable with 100 watts, we will expect the current level to be higher than 1 amp. But this can be provided, I don't know them by heart, but this can be provided after the webinar.
Okay, great. Good. Thank you very much. Next question. Are there thermal modeling programs available that could show similar results and be used to estimate derating performance of cables? And if so, can you provide info on the modeling software?
Well, there are a couple of software that can be used for thermal modeling. We've used COMSOL in the past, and I believe there are a couple of models too that can be used. In IWCS proceedings, there are a couple of models there as well.
Okay, thank you. Next question. Was the return loss effect of heating permanent after cooling?
Was the what? Sorry, can you repeat that question again?
Yes. Was the return loss effect of heating permanent after the cooling?
Yes, it was a permanent reduction in the return loss as we have observed in this presentation.
Okay, thank you. Next, for the thermal variation tests, what was the cable primary insulation material?
The insulation material.
Yes.
I don't know the insulation material. Actually, this cable, one of the cables lying in the lab, we didn't manufacture the cable, so I wouldn't know the type of insulation, the dielectrics that was used on the conductor. I don't have the information.
Okay, and last question. For the 6A testing, what was the material of the wire insulation, the cable jacket? It sounds like you already answered that question.
Yes.
Okay. Florence, thank you for presenting this very interesting and important topic today. Please note the contact points being shown should you wish to contact Florence after today's event. Each of these IWCS webinar series presentation events are recorded and will be archived on the IWCS.org website. It normally takes up to 2 weeks for these to be posted. The IWCS webinar series will conduct presentation events on a monthly basis. Webinar events will take place on the third Friday of each month at 10:30 a.m. Eastern USA time. Our next scheduled webinar event will be on Friday. Will be announced soon. Each of you will be receiving an announcement for the event a few weeks prior. Please feel free to share our announcements with your colleagues so that they can join in and register as well. For over 66 years, the IWCS International Cable and Connectivity Symposium has been the recognized leader showcasing new technologies in cable and connectivity products, processes, and applications. Our next annual international conference will take place on Sunday, October 14th through Wednesday, October 17th, 2018, at the Rhode Island Convention Center in Providence, Rhode Island, USA. In addition, our second annual regional UL and USA China 2018 Cable and Connectivity Symposium will take place on Tuesday, March 20th through Thursday, March 22nd, 2018 at the Shanghai International Convention Center in Pudong, China. Please visit our website at iwcs.org for more event details. In just a moment, you will see a brief survey so that you can provide us your feedback and comments on today's event so that we can further improve this webinar series for you. Thank you for participating, and this concludes today's event.